I will start to upload the recorded lectures to YouTube. So you will start to see links for these lectures under the virtual classroom section on e-learning. And for starting from today, actually, I did not schedule this meeting on Zoom through e-learning. What will I do for the coming few lectures, hopefully, is to send you, is what I did today. I sent you the link from the system because some students are facing trouble logging into the meeting or into the class from the e-learning platform. So it is better to log in into the meeting from the Zoom application directly. But I will place the links for the recorded lectures under the virtual classroom section starting this lecture, after I upload them to YouTube, of course, because there's a problem with the system. It keeps the recorded lecture for 48 hours. After that, it drops the lectures, it deletes the lectures. Okay, so let's start our lecture, and we will start as usual by seeing if you have any questions. Any questions? Last lecture, we just talked a little bit about interfacing switches, dip switches, push buttons, or basically single pole, single through switches. And then we moved to chapter 5, where we talked about programming using C language to program the HCS12 microcontrollers. And as we said, basically, the idea is you need to know some basic knowledge in C programming in order to write program. For example, you need to know the structure of the program, how to define a function, the main program, how to define variables of different data types of different sizes, to know the basic operations, arithmetic and logic operations, and to know the basic control statements, which are the if, for, while loops, and all that stuff. And I believe most of you, they know it, either from C language or in Java or any other high-level language. So what is new in that chapter? What was new is how to deal with the things related or that are specific to the microcontroller, such as the ports, configuring the different features, and so on. So we saw different examples, and I kind of closed the discussion on chapter 5, but I skipped one small topic, which we already discussed when we talked about assembly programming, and that, let me just share the slides. Chapter 5. Okay, I will share the slides now. You can see the slides. So basically, we talked about very quickly about all this stuff, and I skipped very small thing here, which is the time delays. We talked about time delay when we talked about assembly programming, and simply in order to generate time delay, we simply wrote useless, a set or a sequence of useless, non-useful instructions to waste the execution, to waste the time of the microcontroller. Excuse me, to waste the time of the microcontroller. The most important thing there is these instructions do not change the state of my program, and they simply take some cycles to execute. So the way we designed or we calculated or we designed the delay sequence is basically to know what is the number of cycles each instruction needs to execute. So we counted the cycles, then when we multiplied by the cycle time, which is E divided by 2, if you remember, or 2 divided by E, 2 divided by F, I'm sorry. So we multiply by the E cycle, which is half the frequency of the crystal oscillator that clocks the microcontroller. Now, if we are programming in C language, which is a high-level programming, we we will encounter the same thing. We might need to write delay sequence or delay instructions to delay the execution of some task after the finishing the current task. So the question is now how to do that in high level, how to do that in C, how to generate software delay in C, how to generate software delay in C. Okay, it was kind of straightforward to do that in assembly because in order to generate certain delay, we need just to count the number of cycles that we want, that we need, then we multiply it by the cycle time. However, in C, we write at higher level and we leave it for the compiler to generate the corresponding sequence of assembly instructions and machine instructions. So effectively, when we write some statements at C level, and we compile, then we execute, download our program to the microcontroller, and we start the operation, the execution of the program. We don't actually know how long will this sequence of delay instructions will take because we did not write the assembly instructions that correspond to this delay. We wrote the high level statements that we expected to generate certain amount of delay, but we left it for the compiler to generate the appropriate sequence of assembly or low-level instructions to do that. So the idea here, how to write code at high level to generate delay. If we know that it is the compiler who will generate the corresponding assembly instruction. And basically the generated sequence of instructions will be different from one compiler to another, which implies the number of cycles that are required to execute this sequence of instructions or this sequence of instructions will be different, and thus the delay will be different. Actually, we don't have any choice other than we time the code that we write at C. We time the code that we write at the C level using simulator. Where, for example, in Code Warrior, you can write your program, you can write the delay function, and then you put a breakpoint before the delay, before calling the delay function, and after returning from the delay function, and then you look at the number of cycles that were required to execute this part of your program, which is the time by which you enter the delay function and the time you exit the delay function. So we know the number of cycles, we know the cycle time. So we say this delay function in C level will result in this number of cycles, or this delay time if we know the cycle time. So this is very important because compilers, because it is the responsibility of the compiler to generate the assembly code. We don't know the number of cycles that will be consumed by these instructions. So, and one more thing, different compilers produce different sequence of instructions. So if we want to write a delay function in C, we need to time it. We need to profile it using the simulator in order to know the number of cycles. So basically, we write the code in, let's say, in Code Warrior, we compile it, then we simulate it to see how many cycles will take, will be required to execute the delay function. And we start to play around with the statements inside that function in order to get the required number of cycles to generate the required delay given the cycle time that we have. So this is very important. In assembly, we need to write the instructions, and we need, we know all the cycle per instruction, so it is straightforward to do the calculation. However, in C, we cannot do that because it is the compiler who generates the sequence of instructions. So for here, here we have an example. Write a C program to toggle all bits of port B continuously with a 250 millisecond delay. So what we want to do here is to make Yes, yes, and go ahead.
Should I speak English or in Arabic?
I'm speaking English because, yeah, you can. Okay, you can ask in English.
All right. About the delay in assembly, we were taking care about the frequency, right? About
Yes.
the oscillator, but in C there is no such thing. I care about the.
No, in the simulator, you can tell the simulator what is your clock.
Yeah. Okay.
And if you were listening, I said when you do the simulation, you can count the number of cycles. It gives you the number of cycles required to execute this portion of your program. So this number of cycles, you just multiply it with the cycle time that you have, you get the time delay. But anyway, in the simulator, I think you can set the clock frequency so you can read the time required to execute the code.
All right.
Okay?
Yes.
Okay, so in this simple program, what is required is to toggle all bits of port B continuously. So we make them all on for 250 milliseconds, then all off for 250 milliseconds, and so on, assuming that the bus frequency is 2 megahertz. Bus frequency or the E cycle. This is basically, bus frequency is meant to be the E cycle. Oops. Okay, the E cycle, which is half the frequency. So straightforward. Here he defined void ms delay, which is let me just put the mouse because this one is not working. So here he defined the function prototype void ms delay. So this function basically returns nothing, and I pass to it an integer value. Then we have the main program. He defined here. He configured port B or pins for being all output. Then he will perform what is required continuously forever. So this is the main task of the program is put inside an infinite while loop. Configure it is toggling. I'm sorry. What he meant by toggling here is to make the odd pins on for 250 milliseconds, then the even pins, and so on. So he outputs here 55 hex, then delay 50 milliseconds, 250 milliseconds, port B AA, which outputs AA. So now the odd pins are ones, then delay. Now, this is a function to generate the delay. And if you look at this function, it is basically, it can generate a delay that is multiple of 1 millisecond. So here you pass integer I time. So here you specify how many milliseconds you want to do or you want to execute. So basically, there are two nested for loops here, and they are empty loops. There is nothing inside these loops, and they will execute for a certain amount of time. Now, how did he know that the execution of this will take 1 millisecond? 1 millisecond if I time is 1. If I time is 1, basically he profiled the code. He simulated the code and he calculated the number of cycles, assuming that the clock is 2 megahertz to make the base time here 1 millisecond. So basically, if you repeat it I times, then you will get I times milliseconds. So here he is passing 250 to indicate it is to repeat the inner loop, the outer loop, I'm sorry, 250 times, and this will be equivalent to 250 milliseconds. Yes, Marwan, go ahead.
دكتور شو الداعي انه نحط unsigned int فيها؟
unsigned integer where in the function declaration.
بالظبط.
يعني في النهايه بدك تعرف integer، بس هون انت الفكره انك لو حطيتها negative, if you put here if you define the input variable as integer وشخص راح يستخدمها negative، حط negative value بالغلط, the loop will not execute.
اوكي فهمت عليك.
فلما تحكي له unsigned integer حتى لو حطها integer it will be converted to its equivalent unsigned value. It will be treated as unsigned value.
طب دكتور calling the function ما بياخذ وقت؟
Of course. ما عشان هيك احنا when you profile your code you will put a breakpoint here before you execute this statement, and you put a breakpoint here before you execute this statement. And effectively, the number of cycles shown in the simulator will basically the number of cycles required will be the number of cycles required to call the function, execute its body, and returning from the function. So basically, unfortunately, I'm not able to write on this because it is an image. Let me see if I can do it using this. So you put a breakpoint here. Okay, you execute you simulate your program. When it reaches here, you take the number of cycles. Then when you put another breakpoint when it exits when it comes back from the function, you read the number of cycles. So you have the number of cycles before calling the function, the number of cycles after calling the function. You subtract them. So this will basically be the number of cycles you lost in delaying the code execution. Okay.
اوكي تمام دكتور شكرا.
تمام. And the idea why we declared it as unsigned, as we said, we are working with a positive value always, which is the number, the multiplier of the 1 millisecond. Now, this function, if you take it and try it on your machine, it may take less than 1 millisecond. If you pass I times 1, it may take less than 1 millisecond to execute because the compiler generated different sequence of code. Okay, maybe this code was compiled using the mini IDE compiler, while we have the code warrior compiler. So, but it is not that difficult to modify the numbers here to add some useless statements. Some useless statements inside this function to increase the execution time. Okay. And probably most of you know how to invoke the code warrior in the simulation mode. After you write your program, you compile it, then you run the project in full simulation mode. You can track everything in your program. Okay. Any question?
دكتور الله يعطيك العافية.
هلا صراحة.
الله يسلمك دكتور. طيب هاي بقدر اخذها كانها ستاندر زي لما كنا نعمل في الاسمبلي انه نخليها مالتيبل اوف سم انتجر لما كنا نعمل لود مثلا واي وذ اللي بدي اياه، يعني هاي اعتبرها ستاندر واصير انا مثلا اذا بدي اعمل 250 ملي سكند اخلي اي از ايكوال 250.
لا ما هي انا حكيت the problem here that this function was profiled using based on some compiler. يعني لما تحول this code was converted to assembly. So we executed it. It took 1 millisecond. Okay. As if you take it to code warrior, for example, and compile it, then you simulate it, you may get number of cycles that will give you 1 millisecond if the clock frequency is 2 megahertz. Okay. Or maybe the code warrior compiler will give a different sequence of assembly instructions, and thus the delay or the number of cycles will be different. Okay.
Okay.
Okay, so now, as I said last time, there are many examples in this slide set. Please go over as many examples as you can, just to get familiar with the way of dealing with the ports and working with delays. So all of them are just examples. For example, let's take this one. Here we have an example. We have LEDs that are connected to bits in port B and port A. Write a C program that shows the count from 0 to FF on the LEDs. Okay, so we have a set of LEDs that are connected to port A and port B. So we want to show a counter on these slits. Of course, the two ports are separate, are not connected to each other. So we will show an 8-bit counter on port B, an 8-bit counter in port A. So what we need to do is basically to have some counter, we increment it, we delay it, we show it on the two ports, we delay, then we increment the counter. So here just, and then this is the main function. Configure port B as output, configure port A as output, then set port B to 0, LED equals 0. What is LED? LED, if you go up, it is defined as a constant or a label that points to port A. So it is easier to deal with the keyword LED, but LED here refers to port A. So here we output 0 on port B, we output 0 on port A, which we refer to it as LED. You can do this, or you can do it the same way we did with port B. It's just to show you how you can dereference, or you can label the labeled ports, change the label of the ports. So here we will do this counter forever. So here we have an endless loop, but now it is written in the form of a for loop. If you write it like this, it will be executed indefinitely. So here we say port B plus plus, LED plus plus. So this will increment port B, will increment port A, which is referred to as LED. We delay 0.5 second. Then we keep doing that. So what will be shown on the LEDs is you are just basically showing the binary value of the counter from 0 to 255, and this will be shown on both port A and port B. Now the delay loop here is the same. The textbook is using this as a template because he designed it and he verified it takes certain amount of time on under using certain compiler and using certain frequency, but this might not work for you. As I said, you need to design your own delay function and use it as a base for you. For example, you may play around to design a delay subroutine for 1 millisecond using your own compiler. You play with the content of that function in order to get certain number of cycles that are, if multiplied by the clock that you have, will produce 1 millisecond, and then you can use that as your base time. You call it n times to get n delay using that function. Okay. Other examples, please go through them. Many examples here, but I want to go with you through an example. This is very important topic, but I will not talk about it. You can easily, why the meeting will end up in 10 minutes. We have a pro. ما بعرف أعطاني message إنه the meeting will end up in 10 minutes, despite the fact I have a pro account. Let me see if we get disconnected, I will schedule a new meeting and send you the link for it. So don't worry. For this thing, which is I/O serialization, basically you have 8 bits and you want to send them out 1 bit after another on one of the pins of the ports. So this is called serialization. You convert the data from being 8-bit together, you output it 1 bit at a time. Okay, so look at these examples. This table is important to look at, is how to reference individual bits in different ports in Code Warrior. So for example, in port A, if you want to play with or change the value of bit number X in port A, you reference it by saying port A underscore bit X. And this label is defined in the include file, in the derivative.inc file in Code Warrior. So this is specific to Code Warrior, which is the one that we are using. The same thing for the remaining ports, but the referencing is different. For example, port H, you reference individual bits PTH underscore PTHX. This is how it is defined in the file. Yes, go ahead.
دكتور بدي اسالك هلا لو بدنا نحط بت اكس واكس تكون فاريبل بصير؟
لا هذا نيم، هذا اسم ليبل. هو حاط لك اكس هي بين الصفر والسبعه، ما بصير.
اوكي تمام.
ما بزبط. Okay. So this, because this, when this instruction, for example, let me remember bit manipulation. Yeah, for example, if you want to set, let's take this one, port B. If we want to set port B bit number, no, it doesn't. It won't work here in C. You cannot have it. You cannot have it as variable because this will be encoded inside the instruction as a fixed value, which is the number of the bit number. Okay. So here we have examples. For example, here port DDR bit 1 equals DDR B and not this. This will configure RB1 as input. Will configure RB1 as input because basically you will AND the content of the DDRB register with the complement of this. So basically you will be setting bit number 1 to 0, and what is set to 0, it is an input. Here DDR bit 7 equals this ORed with this. Or simply you can say DDRA bit 7 equals 1. If you want to set this as output, you need to place 1 in its corresponding place in the direction register. So it's simply, if you write this, remove this, you can set it. Okay, here the same thing, desensor is defined as a label or a constant that refers to port B bit 7, port B bit 1, which are the names of the data bits, data pins of the port. Okay, serializing, this is all about serializing. For this example, please go through it. This is the same example, kind of the same example that we used, we discussed when we talked about LED interfacing, which shows, if you remember, it turns this one, then this one, then this one, this is one downward, then upward, but now it is written in C. So please look at it, compare what we did there to what we have here. Forget about this thing, set clock 8. We will talk about this in chapter 6. This is how to use a clock frequency that is different than the half of the main oscillator frequency. And this is simply a delay function that is written to generate 100 milliseconds. The textbook, the author of the textbook, have it in a file called delay.c. However, this is designed under certain setup in terms of compiler and the clock frequency. So we have to be careful when we use it, if we want to use it, because it might not generate 100 millisecond in our case. So we need to be careful about this. So please go through it. This is the main function. It calls a delay subroutine that is not shown here, I guess. Yes, it is not shown here. And it calls this function, which I told you don't worry about it for the time being. But essentially, what does this what this function does basically is it sets the E clock to 24 megahertz. To 24 megahertz, despite the fact that the main frequency of the oscillator is 16. But we can, as we'll discuss in the second part of chapter 6, we can do this. We can change the E clock to frequency higher than the available or the input frequency using the phase locked loop block that is inside the microcontroller. Okay, what we have here is basically what we did, similar to what we did in the assembly version of this program, where we defined, if you remember, a matrix or an array that contains 12, that contains 16 values, which are basically the pattern that has to be output in the forward direction and the patterns that have to be output in the reverse direction or in the upward and downward direction. And now here it's very important, they are defined as characters. 16 elements, it's an array of 16 elements, and you simply index it. You output it to port B, LED table of I, you delay for 100 milliseconds. Of course, this is very compact in size when it is compared to the assembly version that we discussed earlier. So please go through it. Okay, so now I'll stop sharing this. It seems I need to create a new meeting and send the link to you, because for some reason it's not considering me as a premium account. Despite in the morning I recorded about more than 1 hour, more than 30 minutes actually. So I will close this and I will send you another link to join another meeting. Okay.